So, good day everyone. My name is Maria Karen Mabute, and I will be presenting the information capacity or the channel capacity. So first, let's talk about information theories. So information capacity is defined as a mathematical approach in the concept regarding the parameters and condition that is used in message transmission through communication system. So one of the key scientific contributions of 20th century is the Claude Shannon's mathematical theory of communication in 1948. In 1928, information theorist Ralph V.R. Hartley of Belslav published a book which is The Transmission of Information, where here he proved that the total amount of information that can be transmitted is proportional to frequency range transmitted and the time of the transmission. So we need to say that the total amount of information depends to the bandwidth and the duration of transmission. So here we have the theoretical formula C is equal to 2B. So this formula is used when we assume that the channel is no noise or the noise is absent is totally absent in channel. So C is the channel capacity expressed in bps or bits per second, and the B is the bandwidth of the channel expressed in hertz. So next is this. So this is the noisy channel, no? Where the noise become an issue. So C is equal to the B log of 2, 1 plus S over N, where S over N is the ratio of signal to noise in power. So we have the important terms now. So first is the bits per second or BPS. So this is the speed of data transfer or the speed in bits per second denoted as BPS. So BPS is reciprocal of the bit time t. So let's say we have let's have an example. So let's say we have a value of t is equal to 10 micro s or 10 microseconds. So using the formula of BPS, BPS is equal to 1 over 10 microseconds, or it is equal to 100,000 BPS, or 100 kbps. let's go back to the presentation. Okay. The second is the baud rate. So baud rate is the number of signaling elements or symbol that occur in the given unit of time, such as ones. So signaling element or symbol is basically a binary logic. So it's between ones and zero. So the baud rate is the reciprocal of the smallest signaling interval. So bit rate, so here we express bit rate here in equals to the baud rate times the bit per second, or the bit rate is equal to the baud rate times log of 2 s. So where s here is the number of state per symbol. Next is the multiple coding levels. So the channel capacity can be modified by using multiple encoding schemes. So here, multiple coding levels po daw ay permits more bits per symbol to be transmitted. So it is expressed in C is equal to 2b log of 2n, where n here is the number of different encoding levels per time interval. So here, given an illustration, we have data to transmit in decimal number. So we have 201. Then it is, when we express it in binary, we have 11001001. So here, the first picture shows the two states or two signaling elements used, and the other one is the four states or the four signaling elements. So here we only use ones and zero as a signaling elements. So when we compute the bit rate, we have only 1 megabits per second, while on the four state or four signaling elements, we have 0, 1, 2, 3 as a signal elements, and the bit rate is equal to 2 megabits per second. So this implies na channel capacity and the bandwidth will be greater if more than 2 encoding levels are used per time interval. So channel capacity or the information capacity or data rate depends on the three factors. So these are the bandwidth, then the number of levels in digital signals, and the level of noise. So level of noise is the quality of the channel. So there are two theoretical formulas were developed to calculate the data rate. So first is the Nyquist bit rate. So this Nyquist bit rate is for the noiseless channel. So it is expressed in bit rate is equal to 2 times the bandwidth log of 2n. So where here the n is the number signal element to present the data, and the bit rate is expressed in bit rate per second. So the other theoretical formula, which is the Shannon capacity, will be reported by Mr. Macalinao.
Hi, my name is Jeffrey V. Macalinao and I'll be discussing about Shannon limit on information capacity. It is also known as noisy channel coding theorem or Shannon capacity theorem. It defines the maximum amount of information or data capacity which can be sent over any channel or medium. The Shannon limit sets an upper bound on how fast we can transmit information over a particular link. So the genetic capacity theorem says that the capacity is equals to bandwidth times the logarithm of 1 plus s over n, where s is the received signal power at the receiver and n is additive Gaussian noise. So as we can see, that the capacity is directly proportional to the bandwidth, which makes sense because if we have a wider bandwidth to communicate, then we can send more data. Next, we can see it is the signal to noise ratio or the SNR. If the signal is very strong, then this term will get larger and larger and it will keep going. However, if the noise on the other hand is very strong, then it will get smaller and smaller and it will go to zero. And because of that, there is no way to transmit information over the channel. Now, in reality, there are sort of hard bounds on S. Let's say LTE and Wi-Fi have limits on how powerful they can transmit, and those limits are important. Why? Because if the Wi-Fi card, or let's say if the Wi-Fi card could transmit infinitely loudly, it could interfere with lots of other devices, and then interference will actually cause their performance to degrade. So having that said, there's some level at which we cap the signal power of these devices, and also there's some amount of noise that's sort of inherent to the wireless environment. Now we can use this theorem to determine what the upper bound is given a transmitter that can transmit at a certain strength and given a certain amount of noise that we can expect in the environment. So among the points that I have discussed, the interesting part here is that this theorem tells us how much farther we have to go. For example, if you build a wireless system and you measure how much information is able to send and you get only half of the Shannon limit, then you will know that there's a lot of more capacity out there. And you can find any ways on how you can do better, like in encoding, for example, on how you can transmit more. So moving on to the next slide. Okay. Sampled problems. So here, for a typical telephone line with a signal to noise ratio of 30 decibels and an audio bandwidth 3 kHz, find max data rate. So we all know that the formula is capacity equals to bandwidth logarithm of 1 plus s over n to the base of 2. So the given here is the signal to noise ratio, which is equivalent to 30 decibels, and the bandwidth, which is equivalent to 3 kHz. So we all know that the signal to noise ratio must have a unit of watts. So to convert 30 decibels into watts, 10 decibels is equals to 10 raised to 1 watts. 20 decibels is equals to 10 raised to 2 watts. And 30 decibels is equals to 10 raised to 3 watts. So we will gonna use the 10 raised to 3 watts as the given is 30 decibels. So C is equals to 3 times 10 raised to 3 logarithm of 1 plus 10 raised to 3 to the base of 2. As we calculate that, the answer is capacity is equals to 29,901.68 kilobits per second. And that's how we compute capacity. So, for the next example, for a typical telephone line with a signal to noise ratio of 20 decibels, what is required bandwidth to achieve the maximum data rate of 2 Mbps? So here, it is different because the given is signal to noise ratio, which is 20 decibels, and the capacity, which is the 2 Mbps. So the question is, what is the required bandwidth? So we need to find bandwidth. SNR equals 20 decibels. So 10 decibels is equals to 10 raised to 1 watts. And 20 decibels is equals to 10 raised to 2 watts. So we will gonna use the 10 raised to 2 watts. Then we will transpose it. So 2 times 10 raised to 6 equals to b logarithm of 1 plus 10 squared to the base of 2. And that, to find the bandwidth, we need to divide both sides logarithm 1 plus 10 raised to 2 to the base of 2. So we will gonna get b, or bandwidth, is equals to 2 times 10 raised to 6 over logarithm of 1 plus 10 raised to 2 to the base of 2. And as we calculate that, we will have an answer of bandwidth is equals to 300,380.97 Hz, or equals to 300.38 kilohertz. And that's the answer.
So let's solve some problems. First is the communication channel is having a bandwidth of 3,000 Hz. Then a transmitted power is such that the received signal to noise ratio is 1023. The maximum data rate that can be transmitted error-free to a channel through the channel is. So let me share some my whiteboard. So first is we write the given. So we have the given value for the bandwidth. B is equal to 3,000 Hz, and S over N, signal to noise ratio, is equal to 1023. So we will finding what is the maximum data rate to be transmitted in error channel. So C is undefined now. So using the formula of the information capacity or the channel capacity, C is equal to B log of 2 1 plus S over N. So substituting the formula, the given 3,000 log of 2 1 plus 1023 is 1024. So I'll just simply verify it na already. So C is equal to log of 1024 is actually 10. So 3000 times 10. So the final answer, C is equal to 30,000 BPS. So the maximum data rate is 30,000 BPS or 30 kbps. So next problem. Next problem. Okay. So yeah. Next problem. Okay. All of these problems were from the textbook.com. So the second problem, we wish to transmit a digital voice at 32 kbps through a communication channel having a bandwidth of 3000 Hz. The received signal to noise power ratio is 30 dB or 30 decibel. State which of the following statement is true. So here, to explain the question, no, a maximum amount of information on the data rate which can be sent over any channel or medium without error daw. So, ang sasabi lang is, break po tayo sa ating whiteboard. Ang ating data rate, so let's say R, must be less than or equal sa ating channel capacity. So, sulat natin yung given. B is equal to 3000 Hz. And then we have the Sn over n, S over n, 30 dB. So this is in decibel. So we need to convert it in Sn ratio, no? So the formula for this is 30 dB is equal to the 10 log of Sn S over n. So doing the math, S over n must be equal to the anti-log 30 over 10. So S over n is equal to S over n is equal to 1000. So we're gonna clear it. Yeah? So we have here R is equal to less than equal C. The given bandwidth is equal to 3000 Hz. And then the SNN, which is nasolve na natin kanina, is equal nga sa 1000. So unitless. So finding the C, no? Using the formula, C is equal to B log of 2, 1 plus S over R, N, S over N. So C, plug in the given 3,000. Log of 2. So 1 plus 1,000 is 1,001, no? So log of 2 times 1,001 is actually okay. 3,000 times the log of 2 of 1,000 is actually equal to 29.90. So as we can notice, no, C is less than R. So mas mataas pa rin yung R sa C, which means that error-free in transmission is not possible. So that's all. Thank you.